Alright, in this video we're going to talk about just some of the basics of polynomial functions and what a polynomial is. So in this box here we have basically the generic form of what a polynomial looks like. Each of these a values is a coefficient, and then you have times x to some power, and that power decreases all the way down until you get to your constant term that has no variable term with it. So that's basically what this is saying here. The a's are the coefficients, a0 is the constant term, and then an, this leading one, we're going to call it our leading coefficient. And we are going to do some things later on when talking about polynomials where it's important that we look at the leading coefficient and the constant term. So make sure that you know where those are located. Here's an example of a polynomial. We have 6 terms here in our polynomial, but our leading term is 3x to the 5th. Our leading coefficient is 3. Our constant term is -6. But this would be an example of a polynomial. When you graph a polynomial, which I will get into more in later videos here, but when you graph a polynomial, they are always what we call smooth curves. That means that you don't have any breaks or jumps or asymptotes. You also don't have any sharp points. Like an absolute value function comes to a v, comes to a point. We don't have any of those when we graph polynomials. So you're going to get things like lines actually are polynomials. So you can get a line. You could get a parabola, whether that parabola goes up or down. You can get a parabola, it's a polynomial. You could get something that kind of does something like that. That would be an example of a polynomial. It could even be more drastic in the middle here. It could do something like this and then continue to go up and down and so forth. It could do a lot of that in the middle. It could do something like this and then continue to go up. So you can have a lot of different things, graph shapes, I guess, but in general you need to know that they are always very smooth. We call them curves, even though they might not necessarily look like a curve to you. But very smooth curves. Again, no asymptotes or anything like that going on with polynomials. When you graph a polynomial, really it's just a transformation of the parent function. So what I mean by that is, number 1 here, p of x equals -x to the 3rd. That is just this y equals x to the 3rd, but then reflected as our transformation, reflected about the x-axis, right? So reflected about the x-axis. To show you that, I already have graphed y equals x to the 3rd, and then y equals -x to the 3rd is simply just a reflection of that about the x-axis. So this gets reflected down here, and this part here gets reflected up here. The next one that we have is q of x equals x minus 2 to the 4th. That is just y equals x to the 4th, but then that minus 2 on the inside is a translation to the right 2 units. So a translation to the right 2 units. So we look at y equals x to the 4th. It looks something like that. Kind of parabolic in nature, like y equals x squared. It's a little bit flatter at the bottom though. But if I do y equals x minus 2 to the 4th, it just takes that graph and translates that to the right 2 units. And then our last one here is r of x equals -2x to the 5th plus 4. So our parent function here is y equals x to the 5th. And then what kind of transformations do we have? Well, the 2, just the 2 is a vertical stretch by a factor of 2. The negative in front, that is a reflection, just like number 1 here. That is a reflection over the x-axis. And the last part, this plus 4, is then, after all that, a translation up 4. Okay, so we've got a stretch by a factor of 2 vertically, a reflection over the x-axis, and then a translation up 4 units. So I'm going to show you that step by step so you can follow that. If we just graph the parent functions, y equals x to the fifth, which looks like that. If I then apply the stretch of a factor of 2, notice what happens is, it's very subtle here, but if we zoom in you can see it a little bit better. It's a very subtle vertical stretch is what's happening there. It's taking our y values and doubling them, essentially is what's happening. So it's stretching it out vertically. And then we apply the negative to that, which would reflect that about the x-axis. So that red graph turns into the blue graph at this point. And then the last thing is we take that and we move it up 4. And so I'll zoom out so you can see that, but that's just taking that blue graph and translating that 4 units up. So if I get rid of the middle parts here, we take the parent function y equals x to the fifth, and we simply just do all of those transformations, and we end up with this green graph, which is a vertical stretch, then reflected and translated up 4 units.